Good morning, everyone, and thank you for joining us for the second of our Industrial Transformation Research Hub webinars. Today's presentation will be from Dr. Anastasios Polyzos from the University of Melbourne, otherwise known as TASH. Tash will be speaking about, I'm actually going to give his old talk title because he has changed it, but he'll introduce that. So, new approaches to reaction discovery by harnessing visible light, photoredox and enzymatic catalysis. I will, before Tash starts, so I'll just remind people that we've got a series of webinars that the notice for which has been sent around, and it's also up on our YouTube channel. So hopefully everyone has the link to our YouTube channel. The webinar recordings for each session will be uploaded there as soon as possible after the webinar, so you can go and revise or catch up on things that you may have missed. Please subscribe to the channel, and also please like us if you can. It's always nice to know whether you're appreciating the content that we're putting up. But rather than prolong any further, I'll let Tash take it away now and let you know his new title and all of the nice chemistry he's been doing. Thanks, Tash.
Thanks very much, Liz, and thanks for the kind introduction. And thanks everyone for joining us today for the second webinar in the series that Liz has put together. My name is Tash, and I am a synthetic organic chemist. And today I want to talk to you about the capabilities that we have in our group, which will be supporting the activities in the centre, and primarily focused on flow chemistry, photoredox catalysis, and some of the innovations and contributions we've made in that space. And what I really want to do is touch on how we can interface some of these capabilities with the biocatalysis that's being proposed in this centre, and also use that as an opportunity perhaps to discuss what might be viable for each of your research programs and how we can extend this into some projects in the future. To give you an overview of our research group, we are interested in developing methods for synthetic organic chemistry, and the tools we use primarily are photoredox catalysis and flow chemistry, and more recently we've entered into the field of electrochemistry. The key reactions that we are currently interested in involve radical carbonylation chemistry, so that's the installation of a carbonyl group using carbon monoxide gas as a starting material. This can also be used to label molecules, and we've got examples of those, which I won't show you today. However, we also are very interested in the functionalization of olefins and double bonds in molecules. These could also be heterocyclic systems in which we introduce a single electron and undergo single electron reduction, and then further functionalization of multiple double bonds in target molecules. We're also very interested in CH activation chemistry, and primarily around this area, we look at high valent palladium catalysis, which we induce with visible light energetics. And finally, I'll be touching on flow chemistry and automation, which are the aspects we've been developing in our group over the last 10 to 15 years. Okay, so the first topic centers around technologies and flow chemistry and why they're important. So if you consider traditional organic chemistry in terms of target reactions and target synthesis, these are the protocols that we generally follow. We will do one reaction once a target has been identified. We'll do a single reaction. It could also involve a workup, and then move on to a second reaction, a workup and an isolation, and so on and so forth, until the final product is actually reached. Now, if you cast your minds back to your undergraduate chemistry, you'll remember that doing this type of synthesis is quite laborious. It can also be very labor and time intensive if you're looking to synthesize a target compound. There are some other limitations and some challenges with traditional organic chemistry. One is often around scalability. You could imagine if we're going from a small flask to a larger flask, it does require significant optimization, and then moving on to process chemistry, significant effort is required to re-optimize the chemistry and ensure that it's scalable and also safe. Another parameter which is of considerable problem in synthetic organic chemistry is the isolation steps and the purification. Often this requires chromatography, whether it's automated HPLC type purification or even more traditional chromatography using silica. Does require a significant amount of solvent and expensive waste that's generated as a result of these purification steps. And finally, traditional glassware in most synthesis laboratories is limited by its mechanical integrity. So things such as high pressure or gases, reactions that are undertaken with these types of systems can lead to significant hazards in the laboratory and does require specialized equipment. So there is lots of room to move in modernizing synthetic methods, and flow chemistry is one of the tools that's been used to address a lot of these challenges in modern synthetic protocols, but also in the context of manufacturing and also in library generation in discovery laboratories. For those of you who are unfamiliar with flow chemistry, generally it's a continuous process, and I'm just showing you here what the anatomy of a typical flow reactor would look like. On the left-hand side, it all begins with the pumps, and pumps can be either HPLC pumps, they can be simple as syringe pumps, and in industry, often gear pumps are used at larger scales. You have feedstocks being pumped by the pumping systems, and we require some mixing, and those mixing steps can be passive or active, and there is a significant amount of research that's gone into optimizing the mixing steps. The magic happens, of course, in the continuous flow reactor, and the reactors are usually combined or made with tubing, or they can be other geometries that include channels. And in this case, I've shown you in the bottom here that the flow reactors tend to be made of different materials. They could be made of metal or polymer, depending on the application. In most research laboratories, the internal diameter of the flow reactors is anywhere between 200 micrometers to a couple of centimeters, depending on the application. And the volumes are quite small. In general, they're about 10 mil and smaller. Sometimes the reactions do require a quench step. So if we've generated a product here in the reaction zone, and then it's moved away from the reaction zone, we're flowing along here and we might need to quench a particular reactant, and we can have the ability to do that. And of course, you do require back pressure regulation in flow systems that allows, firstly, the accurate pumping and metering of solvents into a flow reactor. So you need some pressure against the solvent front. And also, if you're operating at very high temperatures, a back pressure regulator stops the solvents from boiling out of solution. And then once the products have been driven through the back pressure regulator, then they're collected and isolated. So the benefits of continuous flow chemistry, of course, are obvious in terms of thinking about scalability. So rather than having to re-optimize and going from larger batch reactors to larger batch reactors, we simply pump for a longer period of time to scale the reaction. In our laboratories, in the many flow chemistry laboratories, it's not uncommon to be able to make kilograms of material using a small footprint batch flow reactor that sits on a bench or inside a fume hood. One of the key parameters of flow chemistry is that there is a significantly large surface to area volume in the flow reactors. That leads to very efficient mixing and thermal control. So it's easy to get heat into a reaction and heat out of a reaction. And that also means that we have temporal control of reactants and products. What I mean by that is once a compound has been made, and you can simply move it out of the way of the reaction zone, it's no longer heated like in batch reactors or treated with energy, and then you have a much cleaner reaction product. Of course, there's a safety aspect of flow. So typically these flow reactors are about 10 mil or smaller. So if there is a thermal runaway or an explosion, it leads to a small pop rather than a big bang or some catastrophic event. And there's obviously less energy and significantly less waste generally because of the efficiency of reactions. One of the key aspects of flow, which has been developed over the last 10 years or so, is the ability to introduce polymer support or solid supported reagents. Within the context of using polymers, for instance, we can have surface functionalization of polymers, whether they're beads or polymer monoliths shown just here on the left-hand side, with a range of surface chemistries. And you could imagine that flowing over these functional groups, such as these basic ones or acid chlorides, or even these nitroxides. It's say you can generate new chemical steps if you put these in line. So you could imagine having a catalytic cartridge, one of these simple omnifit columns that are in line in the reactor. You could mediate one new reaction, or you could even use them for purification. So if we wanted to use these bases or acids to do effectively an acid or a base wash, we can mediate with these polymer-supported reagents in line. Now, this lends itself to conducting multi-step syntheses. So we can do a number of transformations along the flow path, or introduce more pumps to introduce more reagents. And that allows us then to generate complex products in one unit operation, and we can avoid chromatography and have much less waste if we're avoiding chromatography. To give you a few examples of the types of reactions that we have developed in our laboratory over the last few years, one is a Fukuyama reduction. And a Fukuyama reduction is quite a powerful tool in terms of being able to take a simple carboxylic acid and convert it to an aldehyde. If we're doing this using conventional chemistry, reduction to the aldehyde is also accompanied by undesired over-reduction to the alcohol, and then requires further oxidation back to the aldehyde again. The Fukuyama reduction is a catalytic palladium reaction with some additional triethylsilane, but converts the acid chloride into the thioester, and then it reduces the thioester to the component aldehyde with no over-reduction of the aldehyde product, of the carboxylic acid product observed. Now, our thought was to be able to convert this into a multi-step sequence where we could have an inline purification and also remove the need to have commercially available thioesters, or even make them before we submit those to the reaction, and starting from very simple and commercially available acid chlorides. We wanted to have a thioesterification step in one cartridge, not isolate the thioester, flow over a palladium catalyst in the presence of triethylsilane, and undergo a purification to generate a pure aldehyde product in one single unit operation. And we started by looking at the types of catalysts that we could immobilize on a polymer support, and we chose these polymer monoliths. And a polymer monolith is simply just that. It's a single polymer which has been polymerized in one of these omnifit columns, and it's very porous, and it's got a very high surface area. And it could be manufactured by simple materials such as divinyl benzene, which is a cross-linker, styrene, and then a functional group which will allow the palladium to be immobilized onto the surface. Again, these monomers are all mixed in the presence of benzoyl peroxide, heated over 48 hours to generate the surface functionalized. So the ethyl ammonium surface material of the polymer, a little bit of palladium in terms of palladium tetrachloride, a reduction to generate the palladium zero on the surface. This worked reasonably well, but what we found was that there was some blocking over time. So we wanted to move something that was a little bit more porous than the fine channels that were created in the polymer monolith. And we found that using a simple polystyrene resin, in which you could introduce some palladium acetate, and the resin was amberlite XAD4, which is a simple polystyrene resin, and we could capture the palladium nanoparticles in the pores of the polymer, and this allowed us to do the chemistry and avoid any of the blockages that we observed in previous chemistries. And the flow protocol looked like this, where we have in one pump an acid chloride, in another pump a long-chain thiol. We chose long-chain thiols for the thioesters to avoid generating a stench in the laboratory, and we could pump those through a polymer-supported base, this dimethyl amino-benzyl amine derivative, and we could generate the thioester without having to isolate it. There was some of the free thiol still left over, and we could track this out with this polymer-supported scavenger, so this isocyanate, which removed any of the thiol. And then we could flow over the palladium resin, shown just here, where we're flowing in some triethylsilane to affect the reduction. And there's a couple of workup steps here. Rather than doing chromatography, we first of all try and remove some of the leached palladium using this scavenger resin. In this case, we've got this thiol derivative, and then this thiourea, and then we could catch the resin on this benzylamine. So what happens here is that we have the aldehyde condense onto the amine to generate this imine, which is trapped onto the resin, and we could wash any of the impurities into a redirected wash step. Once we've removed all the impurities, we do a simple hydrolysis with some acid to furnish the aldehyde at the end. And this works for a range of reductions, and you can see all of these compounds were generated in high yield with some good functional group tolerance. We were then interested in looking at some more complex molecules, and we had a collaboration with Peter Scammels from the Monash University here in Melbourne, where we were investigating the N-demethylation of alkaloids. And the N-demethylation of alkaloids is important, of course, because that's a key step in their derivatization and elaboration to make further active products. So looking at some traditional chemistries to N-demethylate, of course, you need some classical chemistries, which are also quite hazardous, especially at scale. So some cyanogen bromide or some chloroformates. We wanted to avoid using those types of chemistries, especially if we're considering some scale-up applications. One of the key reactions that Peter Scammels had developed with is Polyzos type N-demethylation, which is effectively a reaction in which the tertiary amine is oxidized to make the N-oxide, and then undergoes reduction with these metals, so iron 2 or iron 0, to liberate the free amine. So what we want to do is generate a flow process where we're doing an N-demethylation in flow. We could start with the amine, use an oxidizing step, not isolate the N-oxide, which is required in the batch process, and then run this over an ion column to affect the N-demethylation. Our process, we investigated initially dextromethorphan, and dextromethorphan is a nice representative alkaloid that we could use. And in this case, we wanted to take dextromethorphan, make the N-oxide, and demethylate. And our entire process looks a bit like this, where we have one channel of the flow reactor with the dextromethorphan. We have metachloroperbenzoic acid, so the oxidant in the next pumping unit. These are mixed in the presence of isopropanol and chloroform in a 9-to-1 mixture, mixed at the T-piece here, and we can generate the N-oxide without having to isolate it at -20 degrees in a 10 ml reactor. We wanted then to remove and quench any of the excess peroxide, and we could do this by polymer-supported DMAP, and that gave a very nice clean product, in which we then sent over another cartridge which has iron and a little bit of sand. We could sand provide some nice porosity to flow through at 80 degrees Celsius, and then we could introduce a little bit more of a amount of iron 3 in a separate stream to affect the full conversion to the N-demethylated product. Now, what you'll notice here is we have a couple of workup steps. We have a diacid here, and that'll remove any of the iron, which might be leaching out of the cartridge here. And we have a polymer-supported base to regenerate the free N-demethylated product here at the end. This was generated in 3 hours overall. If you were doing this in batch, it might take a few days, and we could do this in 75% yield. This is also compatible with a range of other alkaloids, and you can see here without re-optimizing the process, it tolerates these glaucine, atropine, and noscapine reasonably well. Of course, we wanted then to be, rather than having one single step on a natural product, we wanted to make an entire natural product itself. And one of the targets we were interested in were these alcohol citrate natural products. And these alcohol citrates have a range of biological activity, and these include compounds such as trachycipic acid, the citrafungans, the zaragosic acids, and sinatrin, and viridiofungin. But the ones we were very interested in, and I've shown the alcohol citrate unit in blue in each one of these cases, and they've got various oxidation states, but essentially they've just got this carbon backbone with 1, 2, 3 carboxylate units on the substrate. And we're interested in these CJs, so CJ13982 and CJ13981, which were isolated from a fungus, CL5032, and have inhibition of rat liver and human liver squalene synthase. So effectively, they reduce your cholesterol levels similar to statins. And in collaboration with Mark Rizakaza here at the University of Melbourne, we proposed to make these compounds in flow. And our forward synthesis for the multi-step flow reaction starts with this lactone in our flow reactor. So we had one of these commercially available lactones with a stereo center installed in one pump, and LDA for a lithiation step in the next flow reactor. And you can see that we used cryogenic conditions, so minus 78 degrees Celsius, where we could affect the enolization and protection of the starting material to generate this enolate shown just here, this TBS enolate. With this, then, what could undergo a cycloaddition with this internal alkyne, where it undergoes a 4+2 cycloaddition at minus 30 degrees to generate the cyclobutene diester. The cyclobutane diester can then be effectively opened in the presence of methanol and some acid to undergo methanolysis, and we could affect this reaction in 15 minutes rather than a 48-hour batch reaction, just showing how quickly we can accelerate the chemistries by simply moving into a flow regime. That generated the furan derivative shown just here with all the correct stereochemistry and the protection on the alcohol just here. And what we can do here is then remove and replace the tosylate with an iodine using a pseudo-Finkelstein reaction by simply flowing through a sodium iodide cartridge at 140 degrees. We didn't isolate the precursor shown just here. We just had a little bit of base and underwent a zinc-mediated reductive elimination step to reveal the subunit for the alcohol citrate just here. We finished at this step here because cross-metathesis, which was the final step here, was very challenging, and we needed to do that in batch, and we are developing some methods in flow to enable this cross-metathesis reaction to occur currently. But it just shows you how powerful these flow methods can be, and you can see that we are significantly improving each of the batch steps as we're moving along the complexity pathway. All right, so that got us thinking about how we can start thinking about incorporating biocatalysis into our multi-step flow reactions, and these are discussions we've been having with Liz and the team, using our imaginations about introducing some biocatalytic pathways to do chemoenzymatic flow syntheses, and we'll be talking about more of this in a later lecture. But the vision here is to take multi-steps of chemical flow reactions, which include thermal and catalytic steps, and then introduce a biocatalytic step and then further processing downstream to generate the product. Of course, the first question you would ask is solvent compatibility. That's a challenge. I know Liz has been working on organic solvent resistant derivatives of enzyme of P450 enzymes, and we can incorporate those. But in the case where there's enzymes that require a solvent switch, we certainly have the capacity to do that. We can use these types of devices. Effectively, these are inline evaporators. And what we can do is evaporate the organic solvent and introduce an organic step shown just here. If we need to use Liz's enzymes, where we can just simply dissolve some of the organic solvent, all we do is just remove the solvent switch and introduce an aqueous water step here to reduce to the correct concentration so the enzyme can operate. One of the things that we've been thinking about is how do we immobilize the enzyme in flow, and we've been using these types of static mixer technologies in our laboratory to immobilize catalysts. Our vision here is to be able to take this similar technology, which is 3D printed, and allow significant mixing to occur in line to immobilize enzymes. So we could use that, use some traditional enzyme chemistries to immobilization chemistries, and we've got some ideas about some novel supports that we could use in that regard. So that's some of the vision and some of the areas that we're looking to expand into in our collaborations within the centre. One of the things that always get asked about flow chemistry is how truly scalable is it? Well, I can tell you that it's already being used in industry to make tons of material per month. And here's an example of an industrial scale flow reactor. This is about the size of a couple of wardrobes that you would find in your home. And these have got continuous flow reactors through the entire system. There's pumps and settling tanks and everything that you would need effectively to have this chemical factory in a very small footprint. Within the context of continuous flow and API manufacture, there's significant, apart from being able to make thousands of kilograms per month in one of these units, you can increase yields, and of course they're very reproducible, leads to significant significant waste reduction and also energy reduction as well, which is a significant consideration in scaling. So, you know, the vision here would be, can we take some of these technologies and then potentially scale up in the future? But that's downstream, of course, but certainly the technology is available to do that. Okay. All right, so switching gears a little bit, I want to talk to you about our work around photoredox catalysis and how we've been using that to design new reactions. And we're slowly, and recently we've been embarking on new approaches to interface photoredox catalysis and enzyme chemistry. So for those of you that have a familiarity with photoredox catalysis, I'll refresh your memory a little bit and just remind you that photoredox catalysis really is an opportunity to take these small molecule dyes and also some, whether they also be sort of cadmium nanoparticles, we can irradiate those with visible light and then generate some redox events with these processes. So we could have a ground state catalyst, use some visible light, generate the excited state, the triplet excited state, and depending on what else is in solution, we can undergo a reductive quench cycle or an oxidative quench cycle. In a reductive quench cycle, a sacrificial reductant is introduced to generate then the reduced form of the catalyst, then this is highly reducing, and then can then pass on an electron to a substrate and undergo further reactivity. And in the oxidative quench cycle, the opposite occurs, in which the catalyst is first oxidized, a substrate is reduced, and then it's reoxidized, then it's to undergo, have a sacrificial oxidant to return back to the ground state again. There are a number of benefits in doing chemistry in this regard, rather than traditional photochemistry. That means that it allows us to not only engage single electron transfer, but also energy transfer and hydrogen atom transfer for having a multitude of types of reactivities that we can engage for new bond activation and generation. The advantages are we require only a small amount of these catalysts, so usually 1 mol% or less. Mild reaction conditions, so we use visible light photons in room temperature rather than traditional conditions needed for photochemistry that use high energy UV light. And we can tune the redox behavior of each of these catalysts, so it's finely tuned for the reactions that we'll be targeting. With our reactions, as I spoke about in our introductory slides, we're very interested in carbonylation reactions. And what we want to do in this regard is be able to take carbon monoxide as a building block, whether it's unlabeled or labeled, and introduce a organohalide, so very simple building blocks that are off the shelf, carbonylate these to generate an acyl radical, which could then be reacted with any types of nucleophiles, whether they be amines or olefins, to generate a series of products, whether they be ketones, amides, esters, or aldehydes, which can be then further elaborated in subsequent steps or as valuable products in their own right. Now, radical carbonylation is fantastic because you can take, it's a multi-component reaction, it's very flexible, and you can generate the products that I just showed you. One of the first examples was pioneered by Leon Rieu and his group in the 1990s. And what he was able to show is that with some traditional radical chemistry, so with an AIB an initiator and astananes, you could take an organohalide in the presence of a double bond, high pressures of carbon monoxide and some significant heating to generate the ketone shown just here, undergoing via this acyl radical intermediate. More recently, in a desire to move away from these vigorous conditions, two pioneers, Jacobi von Wengelen and also Zhao, showed that you could use photoredox catalysis to take these aryl diazonium salts and generate esters or ketones using simple green or blue light irradiation and commonly available photosensitizers. And this worked very, very well. So we were inspired by this and wanted to elaborate this chemistry and generate medicinally relevant heterocycles. And one of the targets that we identified were these dihydrobenzofuran shown just here on the right-hand side. So what we wanted to do was take the tethered double bond shown just here, and then use these internal aryl diazonium salts, which can undergo reduction with a catalyst. And we wanted to do this in continuous flow to make this a much more efficient and safer reaction. So what we want to do then was to introduce carbon monoxide to the flow reactor. And one of the key technologies that we used here was one of these membrane flow reactors, where we introduce liquid inside an inner tube, and that's a gas permeable membrane. And we use Teflon AF 2400 as the gas permeable membrane. It allows gas, but not a liquid, to pass through the membrane. And we could have all this encased in another tube, and we could pressurize the tube and then control the release of the gas across that membrane and enrich the flow reactor with a predetermined concentration of gas. So we enrich in one stream and then do the reaction in another stream and then to generate the product. And you can see that we were using this iridium photocatalyst as a reduction potential of about minus 1.474 volts. And we use the commercial variant of this reactor, which we purchase from these companies. Our apparatus was generally, everything's pretty much off the shelf except for our photoreactor. So we're using a Unix's flow reactor system, which has a couple of pumps. We use this to control the delivery of a fluid shown just up here. That's sent through our enrichment zone, shown just on the bottom left-hand side of this image. We enrich with carbon monoxide. All the reagents then are sent through the photoreactor and then isolated down at another step. We use very simple technology. We just have a bit of tubing wrapped around a support, and we irradiate with LED arrays on either side, and that's a very effective method to be able to use that as a flow reactor. If we need additional photons, we'll use one of the Kessel lamps to irradiate from another aspect of the tubing. This reaction works quite well. In fact, it's quite efficient in generating some complexity in terms of esters on the annulated side of the molecule. It all works in quite high yield and is quite functional group tolerant. So we can have alkyl halides that are not reduced in the reaction and generate some nice adducts in one unit operation. Okay, and one of the other things that we were very interested in was being able then to move away from aryl diazonium salts. Although aryl diazonium salts are great, they're difficult to handle and some issues with chemoselectivity. So what we want to do was introduce a halogen here where we could reduce the halogen and then undergo the intramolecular cyclization. Now, when we did that, we found that there was no reactivity at all. And the reason for this is this key electron transfer step where we're reducing the aryl diazonium salt from the excited state of the photocatalyst does not generate this aryl radical. And there's a mismatch here between the redox potential of the catalyst and also the redox potential of the organohalides that we're using as starting materials. So that's why we're not seeing any of the reactions. So that got us thinking that most of the photocatalysts which were available at the time were not sufficiently reducing to be able to reduce bonds that we found of interest and would be synthetically useful. So if you consider aryl diazonium salts, they've got a very low redox potential. You can basically look at them and they will reduce. But if you move across to more aryl iodides or benzyl bromides or chlorides, you can see the deeper reduction potentials will stop you from doing any significant chemistry with under photoredox catalytic methods. And if you also look at things such as olefins, shown just here, the deep reduction potentials means you can't engage those in reductive pathways to be able to activate those bonds. So to show you how that works, you can look at the redox potential of these commonly available photocatalysts, and the deepest reduction potential is about minus 0.2. Even though we did look at this catalyst, we weren't able to reduce any of the aryl chlorides in this using commercially available catalysts. And the reason for that is that's because the energy of blue photons, or visible light photons, is not sufficiently energetic enough to allow a triplet excited state to be generated of sufficient energy that will undergo the single electron transfer steps necessary for reduction. So if you consider a blue photon, for instance, that has an electron volt energy of 2.8 volts, and that corresponds to about 2.8 volts in terms of a reduction potential. Now, there are a number of factors where you cannot convert all of this photonic energy into redox energy because typically there's about 50% energy lost by a number of factors, whether that be intersystem crossing or internal conversion, or even degradation of the catalyst itself. So essentially that leads to very narrow redox windows that these catalysts can operate. To overcome these, there's been a number of strategies that have been put in place. And one of the things that was considered was consecutive photon-electron transfer. So just to run you through what that process looks like, you take a photocatalyst and you excite it to the triplet excited state. And then in the presence of a reductive quencher, you can generate the reduced form of the catalyst. If you have an appropriate catalyst, you can then irradiate that in a second time, so that becomes a chromophore, then to take this up to a higher excited state, which becomes highly potently reducing an electron transfer is possible to the substrates that we were looking at before. So examples of these types of systems which undergo this consecutive photon and electron transfer are generally within the realm of organic dyes. So here are some examples, and Burkhard Koenig and his group showed that typical pyrrolene diimide dyes, once they're excited, generate this radical ion, which can be further excited to generate a highly reducing species, so down to about -3 volts. More recently, these cyanoarene type dyes with carbazole groups attached to them can also undergo reduction and consecutive excitation to produce species which can undergo reduction at about -2.8 volts. More recently, David Nusevich and his group has also shown that mesacrylidinium dyes such as this can undergo excitations. Here you have the radical anion, and these are almost reducing as lithium dissolved metals, such as sodium and lithium shown just here. So these are great, but there are some limitations with these. There is a significant rapid deactivation of these radical anions. So that means that these catalysts have a very short excitation time, and that limits the catalyst stability in terms of, and also the ability to use these in some more complex reactions. You could imagine that making these derivatives is also quite challenging, and then also can be insoluble. So we decided to try and figure out if there was a better way to do this chemistry, and there was a little bit of a clue that was sitting right under our noses when we're looking at this reaction just here. And this reaction was the photo-induced reduction of an imine to the corresponding amine in the presence of this catalyst. And this reaction, which we reported a few years ago, we were using the iridium trisphenylpyridine derivative shown on the left-hand side just here, which has a redox potential of -1.51 volts. In the presence of triethylamine, we could undergo consecutive proton and electron transfer to reduce this imine and generate the amine. And this was really key to have this proton donor in terms of the triethylamine, which not only activated the catalyst, but also acted as a proton source in the reduction of the imine. We originally thought that this catalyst was doing some interesting things. So if you look at the reduction potential of the imine, it's got a reduction potential of about -2.18 volts. Yet the reduction potential of the excited state iridium is about -1.5 volts. So that's almost 1 volt difference. So that means this should not undergo spontaneous electron transfer. So that got us thinking about what's actually really going on with this catalyst to be able to reduce something significant as an imine shown just here. Excuse me. So clearly this cannot undergo consecutive photon-induced electron transfer. It just doesn't have the ability to generate the radical anion like these, and so a stabilized radical anion like the other catalysts were shown in the previous slides. What we found that this catalyst does is it undergoes a tandem type mechanism in which the photocatalyst is excited to generate the excited state, and in the presence of reductive quencher, in this case it was the triethylamine, generates a radical ion, but it's a different radical ion than the one that I showed you with the organocatalysts. And this can then undergo consecutive proton and electron transfer from the reductive quencher shown just here, the radical cation, to generate a highly reducing catalyst shown just, a reduced species of the catalyst, which can then undergo secondary excitation and generate the in situ reductant in situ. So the way this works is the ground state photocatalyst undergoes excitation to the triplet excited state. Reductive quencher generates the short-lived radical anion shown just here, where we've got the ancillary ligand with the radical anion. And if there's nothing around below 1.51 volts, what you have is consecutive proton and electron transfer from the radical cation shown just here on the amine to generate this slightly reduced ancillary ligand just here. And this ancillary ligand is a chromophore which can undergo secondary excitation to generate the highly reducing iridium species shown just here. It's got a very long triplet excited state, which is about 2.2 microseconds, so fantastic for catalysis, and a very deep reduction potential of about -3 volts. Catalytically, this is how it operates. We have the first the excited state shown just here, where we shine some light onto the catalyst. In the presence of the triethylamine or any tertiary amine generates the reduced form of the catalyst, proton and electron transfer from the radical cation will generate the reduced catalyst shown just here, undergoes excitation, and then you have electron transfer at this step just here, reoxidation, and the catalyst goes back around again. So there's two separate catalytic cycles that are occurring to generate the deep reductant in a secondary step. To demonstrate how well these can reduce, how powerful reducing they are, we were able to reduce aryl chlorides, isolated bromides, all in very high yields, showing how deep reduction potentials can be accessed from this catalytic system. So we wanted to put this into good use, and one of the reactions that we're interested in is catalytic amide formation. And I don't need to tell this audience how important making amides is, and especially avoiding the use of coupling reagents, which can be problematic, not only in small scale, but certainly in manufacturing. But the development of catalytic amide forming reactions is actually quite a challenging thing. It's one of the quite simple, but it's also a very challenging reaction to do catalytically. Our vision was to be able to take very simple organohalide building blocks, introduce carbon monoxide and an amine, and generate amides using our catalytic tandem photoredox mechanism. To date, there was no real examples of this, so we thought would address this challenge and try and generate diverse amide products using our catalytic system. And effectively, we could take organohalides of deep reduction potential, generate a carbon-centered radical, capture that with carbon monoxide, generate the acyl radical in the presence of an amine, and then generate amide products at the end. And that works quite well. And you can see that we're using our flow system where we enrich with carbon monoxide at 35 bar, irradiate in a second reactor at about 15 minutes, and pressurize to about 45 bar in our flow reactor. We had a little bit of dipere, so a base to an amine to help the catalytic system generate the deep reductant. And you can see that we could generate some very useful type of amide shown just here in the screen from various halides, whether they be chlorides or bromides, with various functional groups attached to them. So very tolerant of potentially reducible functional groups. It also tolerates various amines, and you could generate nice libraries of those. We could also reduce alkyl iodides and generate amines, and also more complex products shown as these cholesterol derivatives just here. Okay, an important thing is scale up, and I touched upon that before. We could demonstrate readily that this reaction could be scaled up. So we have this bocpiprazine, a derivative shown just here. Simply by adding a couple of reactors together using a single pump. And we could also measure a steady state condition using this inline FTIR. We could generate grams of the final product without any re-optimization of the condition. So it scales very nicely. All right, so the final reaction that I want to show you was a reaction where we're interested in the hydrofunctionalization of a double bond. And we were interested in this because we could take very simple and abundant feedstocks, whether they're isolated double bonds or part of a heterocyclic system, and we want to be able to manipulate those into sp3-rich products. One of the classical ways is by treating a double bond with a Bronsted acid or a transition metal, and in the presence of a nucleophile, you have a Markovnikov addition product where you're generating a new carbon-carbon or a carbon heteroatom bond in this fashion just here. More recently, there's also been some pioneering work by David Nishavitz and his team, where he showed that photoredox catalysis can be used to oxidize a double bond and generate a radical cation, and then in the presence of a nucleophile will undergo anti-Markovnikov reactivity because of the radical selectivity, the radical stability of that corresponding radical cation. You can also add radicals to a double bond and have similar sort of anti-Markovnikov addition products. But what's less well explored is the reduction of a double bond to generate a radical anion, and then you're generating a very strong nucleophile rather than electrophile, and you can start thinking about new ways to disconnect and generate bonds. So we wanted to use our catalytic system to generate these radical anion intermediates and elaborate with various carbon-centered electrophiles. Our catalytic systems could easily reduce styrenol, so conjugated double bonds. So in our first reaction, we decided to look at these a little bit further and see how well we could generate the radical anion and elaborate those with electrophiles. But before we do that, we need to do a simple reduction of a double bond and use triethylamine and formic acid to effectively protonate that radical anion to generate the reduced product. And just testing that, we could see that we could take these diaryl alkenes and reduce those quite effectively in high yields. It even tolerated some heterocycle systems, albeit at some lower yields, and we could also tolerate halogens without reducing those. So it all worked quite well for most systems, with the exception of introducing some heterocyclic systems in the substrate. In terms of the mechanism, we did some mechanistic studies, and we showed that we could effectively reduce via this pathway. And the pathway does require initially a protonation step, where we're protonating and generating a stable radical. And this could undergo another reduction to generate this anion, which could be quenched again with a little bit of acid. And that is the overall mechanism that we decided to report in the paper. Okay, so with knowing that we can generate the radical anion, how about generating some carbon-carbon bond-forming reactions? So what we wanted to do was consider that the radical anion was effectively a Grignard equivalent, where we could have a naked anion, if you like, centered on the formal double bond, and we could elaborate this a little bit further. So the overall mechanism, or the postulate here, was to take a double bond, generate the radical anion in the presence of an electrophile. In this case, it was a carbonyl, could be an aldehyde or a ketone, and generate these higher order alcohols. And this could all be done without using traditional Grignard chemistry or lithiation chemistry to effect this transformation. So it's really a new approach to carbon-carbon bond formation. And the reaction that we developed used this amine here as the reductive quencher, and we used ketones and irradiated at 440 nanometers at 80 watts to generate a series of alcohol products from the starting ketones. These were generated in moderate yield in this study, and we needed to have a higher equivalent of the ketone to furnish these products. It's a difficult reaction, and as shown here by David Nishevitz, where he showed that you could do an intramolecular variation of this reaction to generate these cycloadducts. But in an intermolecular fashion, these are quite low yielding reactions. We've improved on this chemistry more recently, where we could improve it. I don't have time to go into it today, but we've put this up on the archive, and it's currently being considered for publication. But we can generate the radical anion, and we can diversify with a series of electrophiles, whether they be aldehydes, nitriles, isocyanates, amines, or even carbon monoxide to generate alcohols, amides and amines, and amino acids of complexity. And this works for all sorts of stages, including diversification of pharmaceuticals and natural product syntheses. All right, so our thinking was, how do we then start thinking about doing this chemistry enantiomer selectively? And rather than using traditional co-catalysts where we can have an enantiomer induction event to generate enantiomer-enriched products at the end, what we've been looking at is some flavin-dependent ene reductase chemistry. So here we would take some flavin-dependent enzymes, which you could use flavin derivatives, which will be your photoredox catalyst. These insert nicely into the binding pocket of the flavin, and then this would create a chiral environment in which we can generate this alkene radical anion. And in the presence of various electrophiles, now we're looking at doing this chemistry to generate sp3 rich and enantiomer selective events through coupling with various electrophiles. So this work is in its infancy. What we're looking at effectively now is working with Colin Scott, who has a lot of experience in these types of systems to help generate these photoenzymes using these flavin-dependent systems. So that's a bit of a teaser of what we're doing at this current stage. All right, so what I'll do, I'll sign off here and thank my group who've been doing all the hard work. A lot of this work has been driven by Dr. Melina Sears, shown just here, and some former students. So Dr. Jose Forney developed a lot of the flow chemistry, as well as Nenad Micic, and Tyra Holmgren, and Timothy Connell, and Andrew Kondopoulos, who aren't shown in this image. I'd like to thank all of our collaborators and funding agencies, and also thank you for your time, and I'm happy to take some questions. So thank you very much.
Thanks, Tash, for a very interesting seminar.